The amount of variation that you expect to see in a sample would be less than the amount of variation that you would expect to see in individuals. This particular effect is the gist of this question. Samples of 5 cans are selected periodically from a canning process that has a, now notice that has a standard deviation of 0.2 ounces. So I'm just going to call that particular data point out there. What will be the standard deviation of the sampling distribution? Now, I wanted to call that out there because what this is saying is that there's some high-speed canning process that when you're measuring the cans, they are naturally going to vary according to a standard deviation of 0.2 ounces, a little bit. Now, that means though, when you pull samples of 5 cans and you measure them, how much do you expect the samples to vary? We need another very important piece of information in order to calculate that, the distribution, the sampling distribution. That would be the sample size. Oh, yeah, I kind of blew right past that. Samples of 5 cans. We use lowercase n, typically in statistical process control, to always symbolize the size of the sample. We need that piece of information to answer this question, because to determine the standard deviation in the sampling distribution, how much would samples of 5 vary? We just have to remember a standard adjustment, essentially. Take the original sample, take the original standard deviation, divide it by the square root of the sample size. So for our case, it would be the 0.2 from here, divided by the square root of 5 from up here. I did that on my calculator, 0.8094. I'm going to be lazy and round it to 0.09 ounces. That is the standard deviation in the sampling distribution. And you can see that effect here. 0.2 ounces was how much we expect individual cans to vary. This adjusts it to advise us how much we expect samples of 5 cans to vary. Notice that the number gets smaller, the variation gets smaller, not 0.2 ounces, but 0.09 ounces.